Welcome back. In the previous lectures, we have discussed the binary phase shift keying modulation technique, under which we have discussed time domain representation, signal constellation, then generation and deduction, and probability of error. Now, the power spectral density of BPSK will be discussed in this session. We know that in time domain, the binary phase shift keying modulated signal is represented by the expression S of t with the help of S1 of t or S2 of t. And S1 of t is a symbol which is used to represent the binary data 1, and S2 of t is a symbol used to represent the binary data 0. And S1 of t can be represented as square root of 2EB by TB cos 2 pi FCT, and S2 of t can be represented as minus of square root of 2EB by TB cos 2 pi FCT. Hence, the BPSK signal can be simply represented as S of t is equal to B of t into cos 2 pi FCT. And the multiplication of cos 2 pi FCT will shift the spectrum from the base band to the pass band, which is centered around the carrier frequency Fc. And in these expressions, EB is representing energy per bit and TB is the bit duration measured in seconds. And TB plays a vital role in determining the data rate as well as the bandwidth requirement. And Fc is the carrier frequency, RF carrier frequency, which is very, very greater than 1 divided by TB. Hence, we can simply write S of t as the product of the base band signal and the high frequency RF carrier signal. So let B of t be the base band signal. So B of t can be represented as square root of 2EB by TB for the binary data 1 and minus square root of 2EB by TB if the binary data is 0. And this will occur over a time interval of TB. Hence, in time domain, the passband data is multiplied with a sinusoidal signal of frequency Fc. In power spectrum, it is represented by the convolution between the power spectral density of the baseband signal along with the power spectral density of the sinusoidal signal. And the Fourier transform of cos 2 pi FCT is 1 by 2 into del of f minus fc plus del of f plus fc, and the power spectral density of the cos signal fct is nothing but the Fourier transform of the same signal, the square of the Fourier transform of the same signal. So it can be represented as 1 by 4 into del of f minus fc plus del of f plus fc. Hence we can write the power spectral density of the baseband pulse function as, the power spectral density of the BPSK signal. The power spectral density of BPSK signal can be represented by S of f is equal to the convolution of the power spectral density of the baseband pulse signal SB of f and the power spectral density of the cosine signal. So the convolution of any function with the direct delta function will shift the entire function towards the location of the direct delta function. So SB of f convolution with del of f minus fc provides SB of f minus fc, and the convolution of SB of f with del of f plus fc will provide SB of f plus fc, where SB of f is the power spectral density of the baseband pulse function and SS of f is the power spectral density of BPSK signal. Now the baseband signal B of t is the outcome of the polar non-return to zero line encoding scheme, which is realizing the allowing of discrete amplitude levels of rectangular pulses through a rectangular pulse shaping function. Generally, the power spectral density, the BPSK modulated symbol is generated by a polar non-return to zero line encoder. Then it is multiplied by cos 2 pi fct. Then we will get either S1 of t or S2 of t. So if the binary data is 1, then it has to produce square root of 2EB by TB. If it is 0, it has to produce minus square root of 2EB by TB. So the random binary data x of n can have two different values, that is plus root 2EB by TB or minus square root of 2EB by TB, depending upon the input binary sequence. Suppose if the input binary sequence is in such a way that 1 0 1 1 0 0 1, then the corresponding random binary data of x of n is square root of 2EB by TB. For 0, it is minus square root of 2EB by TB. Then for the next one, it is plus square root of 2EB by TB. For the next one, it is plus square root of 2EB by TB. Then minus square root of 2EB by TB. Then minus square root of 2EB by TB. Then for the next one, it is plus square root of 2EB by TB, and it is going on up to the consecutive binary sequence. And this discrete amplitude levels representing the polar non-return to zero line encoding is shaped by a rectangular pulse function f of t. Hence, this baseband signal is represented by the convolution of the amplitude levels, discrete amplitude levels, with the rectangular pulse shaping function, which is represented by the expression B of t is equal to summation of n is equal to minus infinity to infinity x of n multiplied with f of t minus n tb, where tb is the duration of a bit. So b of t can be represented as, and writing it from x from n is equal to 0, so it is represented as x of 0 into f of t plus x of 1 into f of t minus tb plus x of 2 into f of t plus tb, and it will go on. And we know that x of 0, x of 1, x of 2 will have plus square root of 2eb by tb or minus square root of 2eb by tb depending upon the binary data present in the binary sequence. And f of t is the pulse shaping function, and f of t is represented by a pulse function which is represented between 0 to tb and having an amplitude of 1. Hence, the time domain representation involves the convolution operation. The power spectral density of this baseband signal is represented by the product of the power spectral density of the amplitude, discrete amplitude function multiplied by the power spectral density of the pulse shaping function. So Sb of f is equal to Sx of f multiplied by Sf of f, where Sx of f is the power spectral density of the baseband random pulse function, and Sf of f is the power spectral density of pulse shaping signal. Let us describe the power spectral density of the pulse shaping function. We know that the power spectral density of the BPSK signal is nothing but 1 divided by 4 in multiplied by Sb of f minus fc plus Sb of f plus fc. Now Sb of f here is representing Xx of f multiplied by Sf of f. So to determine Sb of f, we need to derive Sx of f and Sf of f. So let us start with the different derivation of Sf of f. That is the power spectral density of pulse shaping function. So the pulse shaping function in time domain is represented by a function which extends from 0 to tb, whose amplitude is unity. Which is represented by a mathematical expression f of t is equal to 1 when t is between 0 to tb and 0 elsewhere. The Fourier transform of this function is represented by its Fourier transform expression, which will lead to f of f as tb multiplied by e to the power of minus j pi of tb into sinc of pi of tb, or this can be represented, the sinc function can also be represented as sine of pi of tb divided by pi of tb. The power spectral density for the deterministic pulse shaping function f of t is determined by the average energy of the signal in frequency domain. Hence, Sf of f can be represented as limitation of tb tends to infinity magnitude of squared the magnitude of f of f over TB. And this type of approach is called as periodogram approach, which is the direct evaluation of the power spectral density of a deterministic signal. We know that the f of f as TB into e to the power of minus j pi of TB sinc pi of TB, and the magnitude of f of f is magnitude of e to the power of minus j pi of TB multiplied by TB into sinc of pi of TB. And the magnitude of e to the power minus j pi of TB will become 1. Hence, the f of f square will become TB square sinc square pi of TB over TB. So TB and this square will get cancelled. So we can write f of f as TB into sinc square of pi of TB. Let us start the power spectral density of the random data symbols. The random data symbols x of n depends on the random binary sequence which is given as the input to the modulator. Hence, the power spectral density of any random signal is determined by in two different steps. The first step involves the determination of autocorrelation function of the random signal, and the second step involves determination of the Fourier transform of the autocorrelation function. So the autocorrelation of the random binary data symbol x of n is given by Rxx of k is equal to expectation of x of n multiplied by x of n minus k. And the power spectral density of the random data signal x of n is given by the Fourier transform of Rxx of k, which is represented by the discrete time Fourier transform of Rxx of k, represented by an expression summation of k is equal to minus infinity to infinity Rxx of k e to the power of minus j 2 pi f k TB, where k is the frequency domain variable. And the amplitude of the polar symbol is given by square root of 2 EB by TB for the binary data 1 and minus of square root of 2 EB by TB for the binary information 0. The autocorrelation function of polar symbol is given by summation of the expectation of x of n into x of n minus k is represented by summation of I is equal to 1 to n xi of n multiplied by xi of n minus k multiplied by its probability function. Let us have two different values. That is, if k is equal to 0, this function Rxx of k will become expectation of x of n into x of n, which is nothing but expectation of x square of n, which represents the mean square value of this random function. If k not equal to 0, then Rxx of k is represented by x of n into x of n minus k. That means here, if a binary data sequence, suppose if 10110 is representing a binary sequence, then the random data symbols is represented by square root of 2 EB by TB minus square root of 2 EB by TB plus square root of 2 EB by TB plus square root of 2 EB by TB minus square root of 2EB by TB. Here, this is x of 0, this is x of 1, this is x of 2, this is x of 3, and this one is x of 4. So if k is equal to 0, this is determined by, or xx of 0 is determined by summing x square of 0 plus x square of 1 plus x square of 2 plus x square of 3 plus x square of 4 divided by 5, or otherwise x square of 0 multiplied by the probability and x square of 1 multiplied by the probability, and so on. Similarly, whereas for k not equal to 0, we have to shift and multiply, and then we have to sum it. Hence, let us determine the autocorrelation function for k equal to 0 and for k not equal to 0. Let us take the k is equal to 0. Xi of n will have two different functions, that is plus square root of 2EB by TB or minus square root of 2EB over TB. These are all the two different symbols. So if k is equal to 0, xi of n minus k will become xi of n. So there are two possibilities. If xi of n is square root of 2EB by TB, xi of n minus k will also be equal to xi of n. So xi of n having two possibilities, square root of 2EB by TB and minus square root of 2EB over TB. As there are two possibilities, the probability of these two functions will be 1 by 2 and 1 by 2. So the multiplication of all these will become 1 by 2 into square root of 2EB by TB. 1 by 2 multiplication of square root of 2EB over TB multiplied by square root of 2EB over TB. This is nothing but x1 of n into x1 of n minus k into p1. This is x1 of n, this is x2 of n. This is x1 of n, set n minus k. This is x2 of n minus k. This is p1, this is p2. So 1 by 2 multiplied by 2EB over TB. 2 will get cancelled, so EB over TB. Similarly, for the next one, x2 of n multiplied by x2 of n minus k multiplied by p2 will provide EB by TB. So Rxx of 0 is determined by addition of these two functions. So EB by TB plus EB over TB will provide 2EB over TB. For k not equal to 0, xi of n and xi of n minus k may be same or may not be same, depending upon the binary sequence. Suppose 1 0 1 1 0. If this is the binary sequence, if I shift for one time 1 TB, then it will be 1 0 1 1 0. So at that time, x of n, this is x of n, and this is x of n minus TB. So it may be not equal. X of n and x of n minus may be not equal, or it may be equal. So the possibilities are, if it is square root of 2EB by TB, it may either be square root of 2EB over TB or minus square root of 2EB over TB. Similarly, if xi of n is minus square root of 2EB over TB, then xi of n minus k shifted version may either have square root of 2eb over tb or minus square root of 2eb over tb. As we are having 4 different possibilities, the probability of each function will be 1 by 4. So the multiplication of each of the occurrence along each of the probability of the occurrence is multiplied by its amplitude and shifted versions, which will lead to EB over 2TB and consecutively minus EB over 2TB and consecutively minus EB over 2TB and consecutively EB over 2TB. So the addition of all these things will provide 0, which is representing Rxx of k where k not equal to 0. So Rxx of k can be simply represented as 2EB over TB if k equal to 0 and 0 if k not equal to 0, as represented in this expression. Now the power spectral density of the data symbol is given by the Fourier transform of this autocorrelation function. And the Fourier transform is represented by the discrete time Fourier transform given by summation of k is equal to minus infinity to infinity Rxx of k e to the power minus j 2 pi f k tb, and it is only having Rxx of 0 e to the power 0 and all other value will become 0. Hence Rxx of k is equal to 0 where k not equal to 0. So e power 0 will become 1. So Rxx of 0 will be 2EB by TB and Xx of f is nothing but 2EB by TB. So its amplitude is, this is f, x of f. So amplitude is 2EB over TB. This is the power spectrum of this random function, and the power spectrum of the pulse shaped function f of t is TB sin square of pi of TB. So sin square function can be represented like this. And this is 1 divided by t. So multiplication of these two spectrums will provide 2EB over TB multiplied by TB. TB will get cancelled. So we shall get 2EB sin square of pi of TB. So SB of f can be represented as the same function which is scaled by 2EB. And the power spectral density of the binary phase shift keying signal is given by S of f is equal to 1 by 4 multiplied by SB of f minus fc plus SB of f plus fc as already discussed. So here we have to substitute this SB of f, we will get this expression, and in spectral representation, this will occur in Fc, which is centered around Fc. And this will be Fc plus 1 divided by Tb, and this will be Fc minus 1 divided by Tb, which will cause the bandwidth of 2 by TB, which is equal to 2 RB. So the bandwidth requirement will be the twice of the data rate of the symbol, data rate of the transmission. This is the power spectral density of BPSK signal.